Okay, thanks for that introduction. So today I'll be showing you some of the OpenTect extensions provided by my suite of open source plugins. We'll be focusing on the Mistie plugin, which allows estimation and correction of time and phase rotation misties, the gridding plugin, which simplifies gridding of 2D and 3D horizon data with fault constraints, the GeoPackage and Geotiff export plugin for exporting OpenTect data types to GIS-friendly formats, and the external attribute plugin, which allows Python scripts to be used to calculate seismic attributes. There are also a variety of other tools and attributes included within the suite, but we won't have time to look at those today, but I encourage you to try them out at your leisure. Now, these plugins are available for both Linux and Windows, and since release of OpenTect 6.4.5 can be easily installed from the OpenTect Installation Manager. Just check the wmPlugins option. Version 6.4.14 is the latest release and is the version that I'm demonstrating today. The source code of all the plugins is hosted on GitHub, and it's released under the GPL3 open source license. The documentation is also hosted on GitHub and can be accessed from links in the README of the source repository, and is also accessible from help buttons in the user interface of the various plugins. Windows and Linux binaries for all releases of the plugins can be accessed via the installation section of the docs. However, the recommended method of installation nowadays is by the OpenTect Installation Manager. So let's look at the Mistie plugin. The Mistie plugin provides a tool to estimate time, phase, and amplitude misties from 2D and 3D data, a tool to compute constant mistie corrections for 2D lines and 3D data using iterative least squares, and tools for editing and review of corrections and misties, and an OpenTect attribute to apply those corrections to seismic data. The time and phase misties are computed by cross-correlation of the trace amplitude envelopes. The amplitude misties from the comparison of the trace RMS amplitudes in the analysis window. The normalized cross-correlation coefficient is also saved as part of the analysis and is a good measure of the quality of the seismic tie, with a value of 1 for a perfect tie and a 0 for no tie. The first 5 icons on the toolbar allow you to create, save and modify files of mistie estimates. The calculator icon is used to calculate the mistie corrections, and the Crossplot icon displays an interactive web dashboard of the results. The minus icon activates a filter that limits the scope of the correction calculation and Crossplot display. You access the Mistie Analysis tool using the OpenTect Analysis menu. To commence an analysis, press the new icon of the toolbar. This displays a dialog to set the scope of data for the analysis. This includes the 2D data type and the 2D lines to include, optionally a 3D volume, and the maximum time shift and analysis window parameters can also be adjusted. A limitation of the tool is it can only work with a single 2D seismic data attribute or type at a time. In practical use, I haven't found this to be a significant issue to date. For 3D data input, you can also vary how often misties are estimated along the intersections with 2D lines using the 2D trace step parameter. For each 2D line 3D survey overlap, the average mistie at the tie points is used. So the process of mistie estimation is quite simple. Just select the data to be included, adjust the other parameters if required, and press the Apply button. If we scroll to the bottom of the table, you can see how the 3D data volume is encoded. At this point, the Crossplot tool can be used to quickly review the results. This displays a dashboard in the default web browser with a table of the mistie data, histograms, and a 3D crossplot. The 3D crossplot is good for identifying significant outliers. Now in this data set, there are a number of intersections with low quality correlations. These generally occur in the lead-in or run-out of one or both lines. These include spurious mistie values, especially for the amplitude. To focus on just the reliable intersections, we can filter the data by clicking the filter tool, which is the minus icon, and hiding those type points with a quality or cross-correlation below some threshold. Here I will just use the default of 0.5. The Misties table is updated to only show the filter data, and likewise generating a new crossplot will just show the filter data. Now, when we can see on here, especially when we look at the 3D tool, that there is a definite grouping of which indicates that there is a significant phase rotation difference between the 3D and 2D data. Anyway, proceeding. Once satisfied with the Misties set, the Calculate button can be used to open the correction estimation tool. The main thing to set here is the data to be used as a reference for the shifts. You can forgo selection, and the corrections will be distributed evenly across all of the intersections. In this case, I want to use the 3D data as the reference, so that's what I'll select. The other parameters should generally be fine. Click the Calculate button and a new window showing the computed corrections appears, in which each line has an estimated time shift, phase rotation, and amplitude scalar. Scrolling to the bottom of the window, and as expected, 3D data, which was used as a reference, we see it has now a 0 time shift, a 0 phase rotation, and unity amplitude scalar. The correction window has icons to save the corrections to file for future applications to the data. Before doing that, it is possible to create a new Crossplot report to compare the Misties before and after application of the corrections. So let's do that. It is clear that the histogram of the Z Misties and phase rotation are now tighter after the corrections. Less spread is also evident in the 3D crossplot. Note that you can use the Save Page As menu in your web browser if you want to keep a copy of the Misties dashboard for future reference. We will now save the computer corrections to a file. By default, the correction file is saved in the MISC folder of the survey, with a default extension of MISCOR. The Misties corrections are applied using an OpendTect attribute. In this case, where the 3D survey is the reference, we only need to create a 2D attribute. So let's open the 2D attribute editor, select the wmPlugins option to filter the attributes, and choose the Misties application attribute. The steps are: specify the data type to use as input, specify the Misties correction file to use, specify the corrections to apply, and name and save the attribute and attribute set. At this point, we have the choice of working with the Misties corrected data virtually or using the Processing Create Seismic Output Attributes menu item to make a corrected data type. We'll work with the results virtually and look at the improvement at a typical intersection of the 2D and 3D data. After we load the results and we select the new Misties corrected attribute to display, we can toggle back and forth and see to what extent the tie has been improved by the application of the corrections. Okay, so let's move on to the gridding plugin. OpendTect already has built-in tools for gridding, but the process of gridding a mixture of 2D and 3D data isn't very straightforward. I created the Grid 2D 3D Horizon plugin to have a quick and very user-friendly way to generate a surface approximation to a range of input data, with flexible control over the extent and resolution of the generated 3D horizon. 4 gridding algorithms are included: thin plate splines, multi-level B-splines, inverse distance weighted, and nearest neighbour. The gridding can be constrained using a clipping polygon, and for all algorithms except the multi-level B-splines, fault heave polygons and polylines can be included as gridding constraints. The UI for the gridding tool has 2 tabs, one for setting the input data, which can include 2D and 3D horizon interpretation, as well as polygon and polyline point sets. The point sets add the flexibility for an interpreter to add additional control to guide the gridding algorithm in areas of sparse or missing seismic control. Note that wmPlugins includes a tool that can be used to draw these guide point sets, but I won't be showing that today. The gridding tab controls the grid definition, the choice of gridding algorithm, and the selection of fault or clipping constraints. The definition of the grid extents and spacing is relative to the survey geometry. In this case, it is tied to a 3D seismic survey, which has an inline crossline spacing of 25 meters. So output steps of 10 by 10 corresponds to a final grid spacing of 250 by 250 metres. Grid extents can be determined from the input data, either as a bounding box, a convex hole, or be set to be identical to an existing 3D horizon in the project. Now, the multi-level B-spline algorithm is a fast way to create a simple grid without fault constraints. Thin plate splines generates the best quality grids, but can be slow if the grid steps are small. It also allows the use of fault heave polygons and polylines as fault constraints. Generally, I draw the fault constraints by hand, but wmPlugins includes an experimental tool to generate fault polylines at the intersection of a 3D horizon and fault surfaces if you have them. It is a two-step process. Firstly, generate a continuous horizon using, the multi-level B-spline algorithm. Use the tool located on the Polygon Tree item Tools menu, select the 3D horizon and fault surfaces to use, and specify a prefix to help identify the generated fault polylines. These polylines can then be used as constraints in a final gridding run to generate a quick and dirty faulted surface approximation. I like to use the open source GIS package QGIS to generate and display maps for reports and presentations. I developed the GeoPackage and Geotiff plugins for fast transfer of data between OpendTect and QGIS. Most of you will probably be familiar with the Geotiff georeferenced image format and shapefiles. The GeoPackage database format is an open source multi-layer container for GIS geometries. For those familiar with ArcGIS, it is similar to Arc's personal geodatabase, except it is an open standard and uses the open source SQLite database as a backing store instead of Microsoft Access. The GeoPackage format is better than shapefiles because everything, including the CRS information, ends up in a single file. Multiple tables and object types can be saved into a single file. Compare this with shapefiles where points, lines, and polygons each have to have a separate set of files. It is widely supported as it is an open format. The plugin supports export of all the important OpendTect data items to the GeoPackage container. Note that your project must have been assigned a CRS to use this plugin. You access the plugin from the Survey Export menu item. The GeoPackage export dialog has multiple tabs to select the data to be exported. The survey box, 2D lines, random lines, wells, including well tracks and formation tops, as well as 2D and 3D horizon data are all accessible for export. Today we will export everything except the horizon data. Optionally, it is possible to append to an existing GeoPackage database if you want to add more data later. Geotiff 3D horizon export is also straightforward. It is possible to export the Z-grid and horizon attributes into a single file. So here I am exporting two Geotiff files, one with the regional Z-grid from the previous demo, and an horizon from the 3D survey, which also has associated horizon attributes. All these files that have been created by the plugins can be easily displayed in a GIS package like QGIS. Now, I don't intend to give you a full demonstration of how QGIS and data exported from OpendTect can be combined, but hopefully just enough to get you interested. Let's start with the GeoPackage file we just generated. We just drag the items into the layer box of QGIS and they are displayed. We can adjust the order so items of interest aren't obscured, style the appearance of the data, and activate and deactivate items as required, depending on what we're trying to show on the map. You can also drag in the Geotiff files. Now, the regional time horizon has only a single layer and is best displayed using pseudo-color. We can also use some of the raster tools within QGIS to do things like generate contours. QGIS print layouts provide a way to generate high quality map displays. You have full control of the map area, labeling and map ornaments. And once a print layout is set up, it can be used to generate a suite of maps with a consistent appearance. Now the 3D survey horizon is 3 layers. QGIS has the flexibility to display each layer as a separate pseudo-color image or to actually do color blending. We can also then have a separate layout to display the map of the 3D survey area. Report quality display, in this print layout is easy to achieve. Now, external attributes are seismic attributes computed outside OpendTect in an external process. The process doing the attribute computation and OpendTect communicate using operating system pipes, a file-like mechanism for inter-process communications. This plugin defines the communications protocol and external interface that must be implemented by the external process and includes a reference implementation for Python 3. The plugin supports everything from simple single trace, single attribute input and output through to complex multi-trace, multi-attribute input with multi-attribute output. Generally, an external attribute can be used anywhere a standard OpendTect attribute can. To date, this plugin has mainly been used with external attribute scripts written in Python. In fact, as part of the wmPlugins installation, a folder of Python attribute scripts is added to the OpendTect installation in the bin Python wmpy folder. I actually use some of these quite often. The XLPA Smooth is a very effective spatial noise filter that preserves structure. The correlation script computes local time shifts between seismic volumes. And then there is a series of scripts for computing AVO intercept and gradient from angle stack volumes. If you know some Python, it is relatively easy to write an attribute. Examples in the skeletons folder are a good place to start. To use the plugin with Python, you need a Python 3 environment with the numpy, scipy, and numba modules. I'd recommend installing a modern Anaconda Python stack, but when OpendTect version 6.6 is released, you'll have the option to install a suitably equipped Python environment from the OpendTect Installation Manager. In this demo, I'm actually using the ODML Python CPU MKL environment from an OpendTect 6.6 beta install. Now, the OpendTect 6.4.5 release added a Python settings dialog to specify a Python environment to use. This was primarily aimed at using the PowerPoint export plugin, but those same settings control the default Python environment used by the external attribute plugin. Here is an example of a simple Python external attribute script that takes inline and crossline dip volumes and outputs either the true dip or dip azimuth. The UI of the plugin attribute is described in the xa.params Python dictionary, and it is automatically generated by the plugin. The doCompute function is where the attribute calculation takes place. There is some initialization of constants, and then in this while loop, input traces are read by xa.doInput, some calculations are performed, and the results are output back to OpendTect by xa.doOutput. Significantly, with 20 lines of Python code, of which about 75% is boilerplate, this script achieves what would take several hundred lines of C++ code in a standard OpendTect seismic attribute. Don't worry if all that Python code doesn't mean anything. You can still use the Python scripts installed with the plugin. First, let's have a look at the LPA filter. Open the Attribute Description Editor, select the wmPlugins external attribute. The interpreter field is pre-filled by default with the Python environment in the Python settings. You can override this if necessary. Select the attribute script and the UI for the attribute should appear. If external help exists, there will be a question mark next to the script file, which if clicked will open a browser window showing the link. The LPA filter works by fitting a weighted least squares third order 3D polynomial approximation to a small cube of data around each sample. You control the smoothing by specifying the size of the data cube and the weighting. A size of 2 by 2 by 2 and a weighting of 0.5 generally produces pleasing results. This data is not particularly noisy, but the filter's effect is still apparent. This filter is quite effective at removing noise while preserving dipping events. The correlation attribute script located under the miscellaneous folder is also one I use a bit for assessing the quality of AVO angle stacks. Computing the local time shifts and normalized cross-correlation coefficient between angle stacks and the full stack as reference can highlight issues with alignment of the stacks and variations in wavelet character. It's easy to define attributes to compute these parameters for the near and far angle stacks. These can be assessed by examining them over a few key events in the seismic volume. Here I have already used these attributes with the Processing Create Horizon Output attribute menu to compute them as horizon data. Further evidence that Python attribute scripts can be used just like an OpendTect native attribute. Well, that's all we have time to cover today. I hope it encourages you to install and try out the wmPlugins. If you encounter problems or have questions, you can post them on the OpendTect user group or on the GitHub issue page. I monitor both and will get back to you as soon as my time allows. If you write a killer Python attribute script and would like it distributed with the wmPlugins, I'm happy to collaborate. Just get in touch.